Hello everyone. So topic today I'm going to take is 1.5 sigma shift. This is not a very complicated topic, but yes, many people get confused by this concept, and especially those who are new to Six Sigma or who haven't executed any kind of project in Six Sigma, they normally get just confused by this concept of 1.5 sigma shift. Right, so if I have to just cut the long story short, so exactly what is 1.5 sigma shift? It's a statistical correction which we use in case we are handling long term projects, right, or processes. So in normal words or in simple words, it's a buffer which is created to protect our processes from variation, and this variation is a constant companion of any kind of process or project or anything. It is bound to come in. So this is a buffer, that is 1.5 sigma shift is a buffer which we create. So if I just to give you a simple example of how you can understand that what is this buffer. Okay, just think that you have to go for some work or a holiday to a very remote place. So this remote place doesn't have any kind of access to electricity or Wi-Fi signals or even the food. Maybe you can say some sort of a jungle. Right, so if you have to go for 2 days, I assure you that you're going to pack for 4. You're going to take extra set of clothes, you're going to take your power banks, battery banks, whatever, because you are not sure that how the things are going to turn up there. So this is basically a buffer. Whatever additional preparation you make is a buffer to just save yourself from anything that you're not prepared for, right? So in same way, this is 1.5 sigma shift is what we do to our processes, so that we just prepare our processes, long-term processes, from those unknown variations which may enter. Right, so coming back to the concept, and till now what we have known about Six Sigma, or if you've just heard about all my videos, if you've just seen my previous videos, so basically Six Sigma is a data-based methodology to improve process performance, and this is done by reducing variability and to bring down the number of defects to certain number, that is 3.4 defects per million opportunities. This is our target, right? And this includes 1.5 sigma shift. Now this is something which confuses many, that why we have to bring down the defects to this number, and what is this 1.5 sigma shift. Right, so if you just look at this table, it has the Six Sigma levels and the corresponding number of defect values. Right, so if you just look at 2 sigma, so the number of defects per million is 3 lakh something. If you just look at 3 sigma, it's 66,000 something, and 4 sigma is 6,210. For 5 sigma, this number is 233, and for 6 sigma, this number or the corresponding number is 3.4 defects per million opportunities. And this number is ideally a near zero number of defects. If we can achieve this, this means our processes have near zero defects, like they are flawless. So, but here if I add that statistically Six Sigma value corresponds to only 2 defects per billion opportunities. Now there would be some kind of confusion, because here I am saying that Six Sigma corresponds to this number, but statistically it's 2 defects per billion opportunities. So now what's going on? So basically this ambiguity is due to this concept of 1.5 sigma shift. Right, so to understand this, I'm just going to give you a brief history of whatever is known of standard deviation. So if you just look at old books of standard deviation, you will find the tables which have the value of standard deviation, that is z value of 3, right? But in early 1990s, or you can say 1992 exactly, a book was published in the name of Six Sigma Producibility Analysis and Process Characterization, and this book was written by J. Harry and Ronald Rawson. Right, so in this book they just showed, or this book had a table where they did further analysis, and they showed that the value of normal distribution, that is z value of 6, and there they showed that it's 2 defects per billion opportunities. So now coming back to our concept, Six Sigma we all know is the measure of variation, that is how well our process is working. So if a process is working at 6 sigma capacity, it will be working at an efficiency that has near zero defects, or it has 3.4 defects per million opportunities, right? So now when we compare these things, that 6 sigma value statistically is 2 defects per billion opportunities, and here I am saying 3.4 defects. So basically what I am trying to say you that what I am trying to tell you is that if for short term processes the value of 6 sigma is 2 defects per billion opportunities, and this corresponds to 4.45 sigma for long term processes, right? When we say it's a 6 sigma process, it's for short term processes, and for long term processes same number will be 4.5 sigma level, right? And this includes a compensation factor of 1.5 sigma. Now, to understand why we need this concept, that is 1.5 sigma shift concept, the first thing you need to understand is that the processes are designed, whatever process we are talking about, these processes are designed to meet the specification limits. Now these specification limits can be anything. These can be the customer requirements, the engineering requirements, any limits or anything or any requirements to which the process has to comply, so that it's not considered defective, it's not considered waste. Now even if you have certain kind of like, you have to get certain shirt ready for yourself, so you have certain sizes, right? So those would be the specification limits, that yes, I can wear like if your size is 32, shirt size is 32, so you would say that yes, I can wear up to 32 or 32.5 or 33, and then I can just have like 31.5, but beyond that, that shirt won't fit me. So those are your requirements within which the person who is making that shirt has to make the shirt, only then you will buy it, or you would just consider it as a good product, right? So these are the specification limits, and our processes have to comply to these specification limits. So this is usually shown like this. So this is our average, as I told that your shirt size is basically 32, right? And so the upper spec limit is this, that is maximum 33, or you can say 32.5, and the lower one is 31.5. Anything that goes beyond it, you are not going to accept it, so that is considered a waste. So your processes have to comply to these upper and lower spec limits, these specification limits, only then it's a good process, right? So your target is that your process stays within these spec limits. Best it should be near the mean, that is, it should be like this, a tight process, something like this, which is very near to the mean, but a good process is the one which meet its spec limits, right? So all processes are designed to meet the spec limits. But according to law of thermodynamics, entropy enters. When we talk about long-term processes, entropy enters, and this means variation enters. So in short term, we only just see the chance cause of variation, but in long term, we also have to face the assignable cause of variation. So this variation, this means when it's going to come into our processes, so what would happen? This is bound to come in, and what would happen? Either the process standard deviation would change, that is, this would change, whatever it was earlier, it can change, or the mean of the process moves away from the center. Now if this was mean earlier, right, so with time this mean can move away. It can be here, it can come here, here, or here. So what would happen when the mean would shift, or the specific the standard deviation would change? So fewer standard deviations will come between the mean and the your spec limits. So right, so here they are more, but in this side they would be less. So what would happen is that your process would no more away to these spec limits. It can go out of these spec limits. For example, it can go like this, or it can like be like this. So this means whatever is falling beyond the spec limits, it is going to be a waste. So to accommodate this variation that enters into our processes, or which creeps into our processes, and especially in the long term processes, this concept of 1.5 sigma shift was introduced. And so basically this is basically a buffer which is created. For example, if your spec limits are like this, 33, 32, 31, so what usually happens is that you create a process like this, right? And if this is your mean and these are your upper spec limits or your lower spec limit, so what you would initially try, your target would not be a process something like this, it would be a process like this, so that even if there is variation which is usually counted as 1.5, and if your process shifts to a certain, like it can be here, so even if this shift happens, so what would happen is that your product or processes, they won't fall out, they would be within the spec limit. So that's why we have just brought in this factor of 1.5 sigma shift. So now most of you would be thinking that if we have control limits for this purpose, right, to control our processes, we have control charts so that we can figure out that our processes don't fall beyond these spec limits, then why do we need this number of 1.5 sigma? And these control charts can handle all the variation. So I won't go into much detail over here about why these are not sufficient, but the only thing I would say is that they are not enough. The control charts or the control limits, they are not enough. The reasons are there are sampling errors, control limits will not detect every movement in the process average, there would be variability in the data collection, and then other reasons are also there. For example, in production, oversimplification is the biggest error, as it determines sigma based on short-term variation or data. So here what you do is that you just consider that what is the sigma level based on the data collected on short-term processes. So that's just going to cause problem when you're talking about long-term processes. Then you just measure products or that have never been used, right? So once you use the product, the figures can be different, the data can be different, and not considering all activities of value chain. Now there are many activities which substantially add to variation. For example, shipping, handling, how it's being posted or how it's being just delivered to the customer. There are a lot of things which control charts cannot keep tabs on. And then incomplete understanding of the customer requirements. So basically you exactly do not know what are the exact customer requirements, you are making the product and you just don't keep any kind of just this buffer or a statistical correction, and then obviously it would fall beyond the customer requirements. And not counting in the environmental factors where the product is exposed to or in which product is being used, or you don't consider how your customer is actually going to use or misuse the product. So these are the reasons I can say that your control limits or control charts are not sufficient. You need something so that even if variation is there, then also your processes don't fall beyond those spec limits, and this is the thing that is known as 1.5 sigma shift. I have taken this process and this would help you understand the concept better. So what you can see is that this is a perfectly centered Six Sigma process. So we have our process average, that is mean, here at 100, we have standard deviation of 1, and our lower spec limit is here at 94 and our upper spec limit is here at 106. If I just see this image, what I can see is that the overview is telling me that it's a very good project. It's a perfectly centered, tight process and it's well within the spec limits, right? So now if further you just investigate, so you would see that within 4.5 sigma range here in short term, this represents 99.9997% data. This means it's a very good process, and here we have further a cushion of 1.5 sigma. So even this cushion will help us in case our mean shifts due to any XYZ reasons, our mean shifts and the variation is there, and this variation causes our mean to shift from this place. So what we can see is that it's assumed that maximum shift in this mean is 1.5 sigma. Right, so this is assumed. So even if our mean shifts from here to here, right, so this is like 1.5 sigma shift, even then the complete process will fall within the spec limits. due to this 1.5 sigma cushion, right? So this would help the process from straying away from the spec limits. It would help the process to keep within these spec limits, right? So this is why whenever we are designing any process, we are just designing any product, we're just working on any process, in beginning stages they consider this factor, that is, they just consider this shift of 1.5 sigma, that if variation is there and the mean shifts or some standard deviation goes up, even then the process would stay within the spec limits, it won't go beyond that. So what you can say is that 4.5 sigma plus 1.5 sigma is equal to 3.4 defects per million opportunities over long term, not over short term. In short term it's only the same thing, it's 6 sigma, but in long term this number becomes 4.5 sigma plus a compensation factor. So whenever you're working on any process, we need to consider few things. First, the goal itself is under standard environmental conditions, and changing environmental conditions may result in variation. You know, environment can change, the variation is there, and this variation is compensated using this 1.5 sigma. So your short term goal is equal to long term goal plus an appropriate compensation factor. So what I can say is that if your short term goal is 6 sigma, then your long term goal would be 4.5 sigma, that is your process should be working at this, plus a compensation factor of 1.5 sigma. Now that you have some understanding of what is 1.5 sigma shift, so this concept was given to us by Motorola as long-term dynamic mean variation, right? So at Motorola they carried a lot of research, they analyzed a lot of process data, they studied long-term processes, and finally they reached the conclusion that in long-term processes this shift in mean or variation is somewhere between 1.4 to 1.56 sigma, and for calculation purposes they zeroed on the number 1.5 sigma. So that's how they concluded that what kind of variation is. They just studied lots and lots of process data, and they just studied lots and lots of processes. So as I've already told you that long-term dynamic mean variation, or the variation, the reasons are variation in the process mean over time. So there can be any kind of variation that your mean of the process moves, and then increase in the standard deviation of the process over time, or change in the customer requirements or your machinery or raw material. There are lots and lots of factors which can lead to variation. So now this long-term dynamic mean variation can be due to either one of these or both these factors. So we have to have something which accommodates it, because you know, whenever we carry out any kind of DMAC project, so usually we just finish it within 6 to 8 months. So that's a very short period of process data we have for that particular project or process, and then there we are not, we only have to face chance causes. We do not know what kind of assignable causes will come on and what will happen to the process in long term, what kind of variation can be there, right? So whenever we are carrying out any DMAC process, we always keep this factor in mind, that we need to keep in some compensation factor, so that our processes are designed to just handle this variation. So now I will just briefly recapitulate whatever we did, so that you have the clear understanding. So first thing, whenever we are executing any kind of Six Sigma project, so we are interested in one thing, that is the ability of a process to stay within the spec limits, that is the customer requirements or whatever the process has to comply to, whatever requirements, it should stay within those spec limits. So here if you see, if your process is something like this, so I would say that this is a very ideal process, right? Because it's completely within the spec limits, its mean is in the center. Usually, you know, there can be processes, right? They can be within the spec limits, but they are not centered around mean. For example, they can be like this, or they can be like this, but they are not centered around mean. So what I mean to say is that this is a very, very ideal process, where what you can see is that this is your mean. Here I am saying it's a theoretical mean. So this is the lower spec limit and the upper spec limit, and it's perfectly centered towards the mean. It's within the spec limits, so it's a very ideal process, right? So you can say here this is a 6 sigma process because the distance from mean to both the spec limits is 6 sigma. So this is basically a 6 sigma process, but most processes are not like this. They are either like this, they can be out of the spec limits, or they are not centered towards mean. So there are lots and lots of things. So this is an ideal process. Now what happens is that even if you design an ideal process, something like this. For example, you are just a project manager and you have just designed an ideal process where these are your spec limits and this is your mean, and your process is perfectly like this. So very, very ideal process. So now what would happen is that since it was a DMAC process, you studied this process, you carried your DMAC in 6 to 8 months and you just designed this process. So now what about long term? When this process goes into long term cycles, what would happen? There can be shift in the mean, right? So this mean can shift from here to here, or this side it can shift to anywhere, because variation can enter, and this variation will lead to shifting in mean. Or you can say even if the mean does not shift, your standard deviation just standard deviation expands. So what would happen is that your ideal process would no more be ideal, because it's a good process to begin with, because it's just complying to the spec limits, but it's not a very tight process. You know, if it would have been little something like this, so it would have been a tighter process where there would be space that even if your mean shifts, then what would happen is that if your mean also shifts to some, like say some degrees, or say 1.5 sigma, then also it won't fall, it won't stray out of the spec limits. So your processes should be tighter. But how to design these tighter processes? How will you figure out that, okay, is this process good or not? So basically for this purpose we assume the shift of 1.5 sigma in earlier stages, so that we can place our control limits to some place here, so that if the process just starts just throwing somewhere, we can immediately put our teams into action and they can control this variation. Let's figure out how we can accommodate this so-called 1.5 sigma shift, and why we call that in short term our processes are 6 sigma and in long range the same processes are 4.5 sigma. Okay, so basically performance of a process is measured based on its capability to stay within the spec limits, and this should happen on both sides, either side of the mean, right? And this is known as process capability. I have already covered process capability in one of my previous lectures, and I will be leaving the link in the description box so you can check it for details. So to calculate process capability, the sigma level, that how we do it, how we find out what's the sigma level, it's lower of upper spec limit minus the mean, or mean minus lower spec limit upon standard deviation, right? So whichever is lower, we will keep that one. So I just explain you. For example, this is my process, it's a 6 sigma process and it has a theoretical mean over here. So this is the mean where it should be. But I assume that in long term, in long range, there would be a shift in this mean, because here if you see now the sigma level is same on both sides. So it's a 6 sigma process, so it's 6 on both sides. Because the distance from mean to upper or the lower spec limit is same, right? But in long range, because I am designing this process not only for 4 or 5 months, I just want it to run good enough, it's a long term process. So I assume that there would be a certain shift in the mean, and this can happen on either side, but here I am taking on this side. So I assume that my mean has shifted, right? So this shift is here. And due to the studies carried out by Motorola, what I know is that the maximum shift is of 1.5 sigma. Right, so now this is my actual mean. This is the theoretical mean, but since the mean has shifted, it's my actual mean is now here, and this shift is 1.5 sigma. So if we use this formula, so here I don't need any figures because I have this picture in front of me. So what you can say is that the capability of this process to stay within the spec limits here on the lower side is even greater than 6 sigma. How? Because you can see it is now 6 plus 1.5, so it is 7.5. But here on this side, now it's less than 6 sigma, it's only 4.5, right? So here I would take this into consideration when I have to check my sigma level. So I would be taking up upper spec limit minus the actual this mean, so it would be 4.5 sigma level. So I would take this as my process capability. I would take this section, right, to calculate my process capability. So here what you can see is that the mean shifted and now the new sigma level is 4.5. So basically in long run, to be on safer side, we assume a shift in mean, and that I've already told you is 1.5 sigma, right? So in long run, sigma level of the process would be theoretical sigma level, that was 6, minus shift in the mean, that is 6 sigma minus 1.5 sigma. I have already shown you here. So the answer is 4.5 sigma. So in long range, long run, my process would be working at a capability of 4.5 sigma, right? So here I would like to tell you that this 1.5 sigma shift is just a statistical correction. It's not that actually it's going to happen, but it's a statistical correction, and it's judicious to use it when you're just designing any kind of process, any kind of product, event, anything, because you know when you are using this means you are just keeping in check on all the variations that can really violate your process. They can make it just go out of the spec limits. So it's better when you are designing something, just always assume that there would be a shift of 1.5 sigma and then design your processes so that they comply with their spec limits.